Hello friends, now we are going to learn dynamic programming under that Bellman-Ford algorithms. If you remember that earlier we have already learned Bellman-Ford algorithms, Dijkstra algorithms, right? So Dijkstra is called single source shortest path, while Bellman-Ford is also a single source shortest path. Okay, so if you see that what is the difference between Dijkstra algorithms and Bellman-Ford algorithms, right? If you are saying that both are computing single source shortest path, then there must be difference between Dijkstra algorithms and Bellman-Ford algorithms. Remember that Dijkstra algorithms is going to compute a time complexity and shortest path. Basically, we are focused on a single source shortest path based on only positive weight on their edge. It means distance, time, weight, whatever the weight matrix you have or graph is a weighted graph, that value must be positive. Okay. While when you are dealing with Bellman-Ford algorithms, that Bellman-Ford algorithms deal with the negative weight on their edge as well. It means if some of the weights are positive, some of the weights are negative, it is going to perform the task. It is going to perform the task and will give you the single source shortest path. Remember, in Dijkstra, since all the weights are positive, your distance is going to be positive. Sum of the distance from CT1 or source to destinations all are going to be positive because it is the positive distance. While in Bellman-Ford algorithms, since weight of these edge can be positive or negative, hence some of the weights can be negative as well. Some of the weights can be like distance from source to destinations can be negative. So maybe you will get -1, -2, -3 kind of things. Alright. So let us see how we are going to discuss this. If I am talking about shortest distance can be negative, right? Then remember that if there is a city A, city B, city C, or you call it as a 1, 2, 3. Here from 1 to 2 is, say it is 3 unit. 2 to 3 we can call it as 2 unit, right? And this distance is -4. In this case there is no problem because we are talking about city 1 to 2. What is minimum distance? Minimum distance is 3. Between C2, source is 1, city 1 to 3 is a sum of distance 1 to 2 and 2 to 3. So basically we are going to talk about 1 to 2 and 2 to 3. Hence 1 to 2 is 3, 2 to 3 is 2, hence total distance is 5. If you are going in this cycle, then what will happen? 5 minus 4 is 1. Here we have 1. So next cycle, here is 1. So 1 to 2 becomes 1 plus this 3 is 4 unit. Because you are going to complete this cycle again. What I am trying to say, if cycle of weight is positive, Bellman-Ford algorithm is going to work. Cycle of weight means what? Weight of all the edges present in that cycle must be non-negative. It should not be negative in. Say as for example, here is 1, we have a 2, we have a 3. Say 1 to 2 is 2 unit, 2 to 3 is 3 unit, and this is, say it is 7 unit, right? -7 unit. Then what will happen? If you are going to find out the distance, all of you please focus what we are talking about negative weight. There is negative weight, positive weight. So hence Bellman-Ford can be applied. Yes, one positive and negative we can apply. But Dijkstra we cannot apply because there is a negative weight. But here, if you are talking about the sum of the weight of these cycle is 3 plus 2 is 5 minus 4 is 1. It is positive. Positive weight of cyclic path. But here, if you see that what is the distance from 1 to 2 is 2. 1 to 3 via 2. 1 to 2, 2 to 3 is 2 plus 3 is equal to 5. Now, this is the first iterations. Next, what will happen? Suppose after 3 you are coming back to 1. Because this is cycle. Nobody can say that this is my final answer. It can be increased or decreased. So now 3 to 1 is 7. So 5 minus 7 is minus 2. So here at the 1 we have already having minus 2 values. Then 1 to 2, what will be the values? 1 to 2 is going to be minus 2 plus 2 becomes 0. Look, 1 to 2 was 2, now we are getting 0. Similarly, if you are going with 1 to 3, 1 to 3, it means at 1 we are having minus 2. 1 to 3 can be rewrite either 1 to 2, 2 to 3. So here we have minus 3. And what is 1 to 2? 1 to 2 is 2, right? And 2 to 3 is 3. So total is 2 to got cancelled, 3 unit. Look, here was 5, 1 to 3 was 5. But in this particular case, 1 to 3 becomes 3 because of negative cycle. What will happen if you are going to repeat again this cycle? If you are going to repeat again this cycle. So look, now we are at 0. Okay. So sum up the distance from 1 to 3 is 3. We are here at 3. 3 minus 7 is minus 4. Minus 4 plus 2 becomes minus 2. Now 1 to 2 distance was 2 in first iterations. 1 to 2 distance becomes 0 in the second iterations. 1 to 2 distance becomes minus 2 in third iterations. And similarly, 1 to 3 distance will be 1 in third iterations. So if sum of the weight of the cycle is negative, as many number of cycle you are going to complete, our values will be decreasing, right? Hence, there is no minimum values you are going to find out, right? Because it will tend to complete these weight distance between the cities or vertex will tend towards negative, right? That is why if there is a negative weight cycle, then even we cannot apply Bellman fold. We cannot apply Bellman fold. Okay. Not applied Bellman fold. Here, if there is a positive weight of the cycle, here we can apply Bellman fold. When there is a positive weight, we can apply Bellman fold. If there is a negative weight cycle, we are not going to apply Bellman fold algorithms. So in this case, still there is a solutions, but here we cannot apply Dijkstra because there is a negative weight. We cannot apply Bellman fold because there is a negative weight cycle. Now, remember that to start with any graph, first you have to check how many cycles are there. Whether any cycle is forming negative weight cycle. If yes, then one line conclusion is there is no possible solutions after applying Bellman fold algorithms. We are not going to apply the Bellman fold algorithm to find out any solutions. So just you write it, there is no solutions for the given graph if there is a negative weight cycle. So let us see that. Here we have negative weight and positive weight combinations. So we can see that cyclic means what? It should complete cycle A to B, B to C, C to A kind of things. So here we don't have any cycle because 1 to 2, 2 to 3 and 1 to 3 is there, no cycle. Here, yeah. Where you can check? No, here also we are not able to make a cycle. This particular part, no, we don't have cycle. Here also we don't have cycle. So let us see that is there any cyclic path? No. So we don't have cyclic path in this, hence we can proceed with Bellman fold. If there is a cyclic path, then remember that sum of the weight on their edge must be positive, then only you are going to apply Bellman fold. In this particular case, just consider 1 as a source vertex. Okay, consider 1 as a source vertex. And at the beginning, since we don't have any ideas what will be the shortest distance from 1 to all the vertex. So remember that when you are starting this journey from the source, your distance from home to your home itself is a 0, right? In this case also, when you are starting the journey from 1, it means what? 1 to 1 is remain 0. Clear? So let us see that. I will give you that pictorial representations as well. 1, 2, 3, 4, 5, 6. There are 6 vertex. I have written 6 vertex. This basically we are going to write number of iterations. Okay. This is basically number of iterations. So here is 1, 2, 3, 4, 5, 6. Don't get confused. Number of iterations will be 1 less than the number of vertex. So number of vertex is 6. So number of iterations will be 1 less than that. 1 less than that. Alright. So let us see that 1 to 1. As I said you, source is 1. 1 to 1 is 0. 1 to 2. 1 to 2 direct distance is, see, 1 to 1 is 0. But direct distance, do you have direct distance from 1 to all the vertex? Rewrite it. 1 to 2, direct distance. What is that? 2. Okay. 1 to 3, do you have direct distance? Yes. What is that? 4. 1 to 4, do you have direct distance? Direct distance means there is a direct edge between the source and that particular vertex. So 1 to 4, we don't have direct distance, hence we are writing infinity. 1 to 5, we don't have direct distance, writing infinity. 1 to 6, do you have direct distance? No, writing infinity. So this is the direct distance from the source to remaining all the vertex. 1 is a source. From 1, we are writing all the path. 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6. So this is basically, iterations. First iteration is completed. So first iteration is basically direct distance. Let us see the second iterations. When you are dealing with the second iterations, right, then you are going with 2 to, we are not going to read 2 to 1, sorry, we are writing again 1 to 0. So in next iterations, by using this 2 and 4, 1 to 2 and 3, we are going to use this distance to update these remaining values. If there is a distance from 1 to 2 and 2 to 4, hence you can update. If there is a distance from 1 to 3 and 3 to 5, we can update. Because we are well known values are 1 to 2 and 1 to 3. So we are going to use this to update these values. So let us see that. 1 to 1, can you update? No. 1 to 2, already we are having 2, there is no other way 2. Now 1 to 3, let us see that 1 to 3. 1 to 3, direct distance is 4. But 1 to 2, there is a path and we are here now. 2 to 3, there is a path. And what is the value? Minus 3. So 2 plus minus 3. What is the values? 2 is already known, previous iterations values. And there is a path from 2 to 3, right? Hence it is minus 3. So 2 plus minus 3 is minus 1. Clear? But these values you are going to update with the help of previous iterations only, not based on this. So 1 to 4, 1 to 2 there is a values and there is a connectivity from 2 to 4 is 1. So 1 to 2 is 2, 1 to 2 is 2 and 2 to 4 is 1. Hence value is 2 plus 1, 2 plus 1 becomes 3. Earlier we had infinity. Similarly 1 to 5, 1 to 5 we don't have direct distance. But 1 to 2 we had a values called 2. 2 to 5 is a 5. So 2 plus 5 is 7. So that is one solution. Second is 1 to 3 is 4. And 3 to 5 is minus 2. So 4 minus 2 is 1 to 3 is 4, and 3 to 5 is minus 2. 4 minus 2 is 2. So from this way, 1 to 2, 2 to 5, we are getting 7, and 1 to 3, 3 to 4, 5, we are getting 2. Hence, 2 is minimum, we will go with 2. Because our tendency is to write on going for minimum distance. So from this way we are getting 7, from this way we are getting 2, we have written here 2. Similarly, 1 to 6, by using this 1 to 2 and 1 to 3, can you update 1 to 6? No, because there is no direct distance from 2 to 6, there is no direct distance from 3 to 6, hence 6 will be, 1 to 6 will remain infinity, we are not able to update in these iterations. Let us see that. Again, 1 to 1 will be 0, 1 to 2, there is no way it will be 2 only. 1 to 3, since we already updated 1 to 3, well known distance we have a 2. So by updating this, we are having minus 1 only. 1 to 4, look, here 1 to 3 value is 4. 1 to 3 value was 4, and 3 to 4 value is minus 4. So 4 minus 4 becomes 0. So we are going to update this with these values minus 1 and minus 4. Minus 1 minus 4 becomes minus 5. Okay. Similarly, 1 to 5 is minus 1 minus 2 becomes minus 3, because it is lesser than 2, minus 3. Since in these iterations we have 3 and 2 to 6, so from this side 1 to 4 is 3 plus 8 is 11. This side we have a 2 plus 6 is 8. Till here 2 plus 6 is 8. Now, let us see in the next iterations. Here is 0, here is 2, no change. And 1 to 3 is minus 1, there is no change. Now, 1 to 4 is minus 1, right? So, it is minus 5, minus 1 plus 4, minus 5, no change. Now, 1 to 5 is 4 minus 2. Minus 1, minus 2, minus 3. And here, since this value is minus 5 plus 8 is, minus 5 plus 8 is 3. Here we have minus 3 plus 6 is 3. Okay. Next iterations we are going to perform, but will not have any change. It is remains same. So this is the solutions to Bellman Ford. 1 to 1 is 0, 1 to 2 is 2, 1 to 3 is minus 1, 1 to 4 is minus 5, 1 to 5 is minus 3, 1 to 6 is 3. Is the solutions after applying Bellman Ford algorithms. Here, maybe when you are going to do it, even some values will be changed here and there. But remember that after applying all the iterations, we will be getting the final values remain same. So maybe when you are doing that minimum values, maybe 1 or 2 values will be here and there. But after applying all the iterations, we will be getting the final values same. So as I said you that if number of vertex is 6, so number of iteration will be 1 less. 6 minus 1 is 5. This is the algorithms. As I said you that first we are going to write is the direct distance. So if I, distance of I is equal to cost of Vi, distance from all the remaining vertex to the source, right? So what will happen after that? I to n, maybe 1 is a source vertex, right? From the V to all the remaining vertex you are going to find out. Now k to n minus 1. Remember that one iteration is already done. Direct distance iteration is done. So if you see that our solutions, This is the direct distance. Hereafter you are looking for the indirect distance, k. So 2, 3, 4, 5 is after applying this formula, indirect distance. Indirect distance, what will happen? Distance of direct distance is greater than distance of indirect distance. Means direct distance dist of I, cost of IU. I is the source, U is intermediate distance. If some of the distance are lesser than direct distance, we are going to update direct distance with indirect distance, where you want to say distance of I plus cost of IU. Sum of the distance is lesser than direct distance. So we are going to update with sum of the distance which is lesser to the dist of U. Summary of this is, this algorithm is used to find single source shortest path for even negative weight on their edge but not negative weight cycle. As I said you, Bellman-Ford algorithm is for finding single source shortest path for negative as well as positive weight. But if any graph is having negative weight cycle, then Bellman-Ford algorithms cannot be applied. Hence, there is no solutions for that. Thank you very much.